In this video, we are given our set of vectors in our vector space V, and we're calling this set of vectors S. And W is our subspace of V containing S. We need to show that W contains the span of S. Now, let's see what's going on. You have V, and it's a vector space. And you have W, which is in V, which is also a vector space. Of course, all subspaces of V are vector spaces. And we have this set S in here. Now, if W contains, let's see, W is a subspace and it contains S. Therefore, we need to show that the span of S is in W. Okay, the span of S is in W. Okay, doesn't seem that bad because the span of S is equal to the set of all vectors of this form. A1v1 plus A2v2 all the way down to AKVK such that A1, A2 up to A sub K are real numbers. Let's write the subscript smaller. A sub K are real numbers. Okay. Now, S is a subset of W. Okay, S is a set or W. And W is a vector space. So, it's closed. This set is closed in W. So, for each V sub I in S, which is a subset of W, that is V sub I is in W, AI VI is in W, since W is closed under circle dot. I mean, if you like, I can literally write circle dot. Okay. But now combinations of these, sums of these, also AI dot VI dot plus, I don't know, AJ dot VJ, this is also in S. Well, we don't know what's in, it's also in W. Okay, VI is in S, VJ is in S, but the linear combination is in W. In fact, A1v1 plus A2v2 all the way down to AK V sub K is in W. Because W contains all linear combinations of all of these vectors. W contains linear combinations of all of these vectors, in particular, the vectors inside S. There's nothing complicated about this problem. My advice is to draw the picture. Okay, W is a vector space, so everything in W is closed. S happens to be part, or maybe even all, of the vectors in W. More importantly, linear combinations of these vectors will be in W. I mean, if I told you that W was equal to vector x1, vector x2, up to vector x sub L, you wouldn't say, well, let me just say it slightly differently. Actually, suppose W, well, it contains the vectors in S, but let's not even think about them in S for a moment. So you have vk plus 1 vector all the way down to vector v sub L. These are the vectors that are in W. Okay? The vectors in this green circle happen to be those vectors, and the vectors in W outside S happens to be those vectors. But now forget about the distinction between these vectors and those vectors. If I just happen to pick those k vectors from W, wouldn't you say that the span of that would be in W? That is, if I take linear combinations of just those vectors, it'll land in W, not even thinking that that set has a name? The answer is sure. Okay, there's your proof. The picture, I think, said it all. If you like videos like this, please subscribe to my channel. If you have any theorems you'd like to see me prove, just leave it as an attachment. I'll try to do it. Most of all, as I always state, watch and learn. See you in the next video.